Okay, kids, time for the moment you've all been waiting for, finally using these logs to do something useful. So what we're going to do is we're going to solve exponential and logarithmic equations today. We're going to start with the exponential equations, then we'll deal with the log equations later on. So the idea here is actually really simple. So what we're going to do is we're going to go back to way back when we were solving exponential equations and they had the same base. We could set them both equal to each other. Like if it was 2 to the x equals 4, well, we just had to rewrite 4 as 2 to the power of 2, then x is equal to 2. Life is good. When you can't write them in the same base, then you have to use a logarithm. So the idea is pretty simple. The first point here is just simply reinforcing the idea that the logarithm operation can be applied to both sides of the equation. So if I have 2 to the x equals 5, there's absolutely nothing wrong with me saying log of 2 to the x equals log of 5. Okay, that's totally fine. We can always do that. And it doesn't even have to be log base 10. It could be log base whatever you want. Now the property, the power law specifically, the property log of x to the y equals y log x is crucial in this whole thing, because this is how we can solve for those gosh darn variables up in the exponent spot. So if we were to solve something like this is just continuing along with the same thought. We'd have log 2 to the x equals log 5. The x comes forward here to become a coefficient, I guess. And then we have x times log 2 equals log 5. Once we have that, we can easily get the log 2 on the other side of the equation by dividing both sides, and we have an answer that looks like this. Some people might prefer to use the change of base rule and then write it as log base 2 of 5, but it's okay to leave it as log 5 over log 2 as well. Usually you can solve this with a calculator, but I would say leaving it in this exact form is pretty typical and pretty standard, and sometimes preferable. Okay, just a quick little reminder here. Log 5 and log 2, people get really intimidated by these things. Just remember, these are just numbers, okay? Log 5 is maybe like 0.7 and log 2 is like, I don't know, 0.2 or something like that. But they are just numbers. They have to stay together. You can't split log 5 into like log and then 5. That doesn't work, right? It's one unit, but it is just a funny way of saying a number. It's similar to saying pi, except you would put the symbol pi instead of 3.14. Also keep in mind when you're manipulating equations, they're just like coefficients. Okay, so sometimes generally we write them after the variable, but like up in this step over here, this, if you ever look at something like this and you're getting a little confused, like how do I proceed? Just think, what if this was 2x equals 5? What have you been taught to do? You divide both sides by 2, cancel, life is good. All we're doing now is we're simply saying log 2 times x equals log 5, and then you just divide both sides by log 2 and you get the solution, okay? And then those cancel. So anyway, just a little reminder there. We'll get into some examples and you can see how this stuff works. So example number 1, solve each exponential equation algebraically. Okay, there's actually two different ways of approaching this. I'm going to use the method we're just talking about, then I'll show you a slightly different method here. And there's so many different ways of doing this. I'm going to call this method number 1. So we log both sides. We get log of 6 to the power of x equals log of 50. Now that we have it in this form, we take the log of it. We can also we can move the x to the front. Hi, Chris. I'll get back to him in just a sec. Okay, so we have x times log 6 equals log 50, and now we divide both sides by log 6, and we get this. Okay, and this is fine. You don't even have to solve for it here. If you really want, you can, but I'm actually totally okay if you just leave it in this form. I'm not 100% sure what your textbook prefers, but if you like, you can work it out. You can go, let's just jump over here to Desmos going. And you could just go log 50 divided by log of 6 if you're really aching for an answer, 2.18. Okay, so this is approximately 2.18. Cool. Okay, so that's the main method to solve this. A slightly different method here, so I'm going to call this the log both sides method. So this is logging both sides. a slightly different way of doing this, and this doesn't work all the time, but it does work in this case. This is what I'll call method number 2. A slightly different way is to rearrange into exponential notation. Whoops, I meant to say logarithmic notation because it's already an exponential notation. So another totally separate way of doing this would be to look at this and go, okay, well 6 to the power of x is equal to 50. This actually converts into, so you're going to turn this into logs, and this is where even I, after doing this for so many years, I still have to think about this. So 6 is the base, so we're going to go log base 6. X is the exponent, so it's going to equal x because logs equal exponents, and then you've got 50 here. If you did it this way, you could then use the change of base rule, and we could actually rewrite it as log 50 over log 6. Like that, you get the exact same answer. So both are equally good. Although the simpler, well, maybe not simpler, but the method number 2, it doesn't work all the time. So let's just look at this next example. Okay, so this one's a little bit more complicated. We've got 9 times 3 to the x equals 4 to the x. Now, because there's an exponent on both sides, you can't rewrite it using the logarithmic notation. So that only works when we've got the exponent in one position, and here we've got it in 2, so we've got to do a different strategy. Okay, so in this case, we're going to log both sides, but before we do that, we're going to look at this and we're going to think. If you log 9 times 3 to the power of x, you're going to have to do a little bit of work. You can actually do a little manipulating before you do that. If you see that 9 is equal to a power of 3, you can rewrite it as 3 squared, and this is going to make your life a lot easier. So now we can go 3 squared times 3 to the x, and this will be 3 to the x plus 2 equals 4 to the x. Okay, so at this point here, this is when it makes sense to log both sides. If you go ahead and you log both sides in the first step, you can do it, but you're going to have to deal with like a log of 9 times 3 to the x, and that splits up into log 9 plus log 3 to the x, and that's going to be a nightmare. Sometimes you have to do it, but in this case you don't. So we log both sides, and we get, let's see here, so we're going to go, whoopsie doodle, we're going to go log of 3 to the x plus 2 equals log of 4 to the x. You might notice sometimes I put brackets around the argument, sometimes I don't, sort of just a personal preference here. When I have big arguments, I definitely like to do it. Maybe I can do it here. Doesn't really matter that much. Okay, so the whole reason for logging both sides is we can now use the power law or the power rule, and we can take the entire exponent out front. So it's really important that you understand the entire exponent comes out front. So what this is going to look like, that entire exponent comes out front there, and we're also going to bring it out front there. We don't want any variables in any exponent positions. So x plus 2 comes up front. That's 1 unit, so that definitely better be in brackets. And at this point, I can write log 3. I'm not going to put brackets around that. Okay, the brackets around x plus 2 is super important, and that's a pretty common one for students to forget. Okay, and then the other one, x log 4, don't need brackets around that because it's only a term. Okay, at this point here, now we've got x on both sides of the equation, so this is where people start to have a bit of a heart attack. And don't worry, it's not that big a deal, but how do you get x in one spot? Normally you collect like terms, and what you have here is you've got a situation where you've got brackets. So what you need to do is you need to multiply the log in, and you're always going to distribute you're going to distribute log 3 into the brackets. Okay, so that's going to give us x log 3 plus 2 log 3. And then the other one over here is x log 4. Okay, we're getting pretty close here. I guess I will just move over there. I probably need a bit more room. But we're going to collect all the x terms on one side. So we're going to collect x terms on one side. what we're going to wind up getting is we're going to have x log 3. We're going to subtract x log 4 to get it over here. And then we're also going to take 2 log 3 and move to the other side by subtracting. So it'll be negative 2 log 3. Okay, you always want to get the x terms on one side. The reason you do that is because now you can factor x out, and you can have log 3 minus log 4. That's equal to 2 log 3. Finally, you can divide both sides by log 3 minus log 4, and you can get this here, all over log 3 minus log 4. Okay, so that was the process. So there's always a little bit of debate in the log unit. How far do you go to simplify? If you leave it like this, I'm happy. If you want to keep going, you can. So maybe just in a slightly different color, I'm going to go with the optional simplifying. You can simplify this a bit further. You could rewrite log 3 minus log 4. You could say this is log 3 divided by 4. That is the quotient rule. And if you're really not liking that negative 2 out in front, you could even write it as log of, you could bring this up here to go 3 to the power of negative 2. That would actually wind up being log 1 over 9. So you could write it like this, which might be a little more compact and tight. So this is an optional simplification as well. So I don't necessarily know what form everyone prefers it in. I can say in the past I have tended to see people usually leave it in this form right here. And if you want to work out an actual value, you can. Okay, let's look at this equation here. Hopefully I won't run out of room. These actually get quite large because of all the steps involved, and there's not a lot of ways to shortcut it, unfortunately. So question C, let's actually just make a little bit of a separator here. Question C is similar to the last one with one major key difference. I'm not going to write a bunch of stuff, so I leave myself some room. You can't write 5 as a power of 2, so you cannot combine the two. The best you can do is you can start by logging both sides right away. So what we're going to do is we're going to go log, we're going to use big fat brackets here, 5 times 2 to the x plus 1, and then the other side is log 3 to the x. Okay, so now we're logging this. I cannot use the power rule yet because that exponent of x plus 1 only goes to the 2. It does not belong to the 5, so it's not fair for me to use it. So what I have to do is I have to first use the product rule, where I've got log of 5 times 2 to the x plus 1. This is going to get split up into log of 5 plus log of 2 to the x plus 1. And then the other side is going to be log of 3 to the x. Okay, at this point, now I can go ahead and I can use my power rule where it applies. So here, I can bring down the x plus 1. And then here I can bring down the x. If you have not given any of this a try, I might recommend you trying it from here just to make sure you can do it. Okay, so what we have to do is we now have to get all my x's on one side. Every time you see brackets, generally you're going to want to distribute into the brackets. So this becomes log 5 plus x log 2 plus 1 times log 2 is x log 3, and then I'm going to get everything together. So the left side will look like x log 2 minus x log 3, and then the other side on the right will look like negative log 5 minus log 2. I'm kind of wishing I did it the other way, where I had the x values on the right, but whatever. Okay, now we just factor this thing out. So we factor out an x. I could even factor a negative sign out of that if I really wanted. In fact, I think I will. I'm just going to factor out a negative sign. And then I can get x equals negative. Well, yeah, I'm gonna do 2 steps in one. Okay, so this negative sign right here, this negative sign right here, and these, they're going to switch places. So I'm going to cancel the negative sign on the right by making it just positive log 5 plus log 2. And then on the left, instead of it being log 2 minus log 3, it's going to be log 3 minus log 2. And that's a pretty good answer. And if you want to use the product and quotient rules, you can do that as well. Log 5 plus log 2 is equal to log 5 times 2, which is log 10. And this is actually equal to log 3 over 2. And now that I'm realizing this, log 10, what's the point in leaving it like that? You might as well go 1 over log 3 over 2. Ta-da! There's a good answer. That's that. That's as far as you're going to go with that one. Okay, so here's example 2. This is a similar thing. It's just in a word problem, and it ties back to why this is so useful, how this fits in with the last unit, and even geometric sequences. So let's use the logarithms to determine the number of terms in a geometric sequence. So what we were doing before is we were saying, okay, well, we'll write Tn equals T1 r to the n minus 1. And we were trying to solve this. And we would just say, okay, well, if the first term is 3 and we can see that r is equal to 2, I think that's pretty obvious here, then we just guess and check. But we want to be better than that. So what we're going to do is we're going to solve this with logarithms. So we're going to set Tn equal to that big number, 12,288. We're going to set T1 equal to this, and then this is 2 to the n minus 1. So the way that we solve for this, without guessing and checking, a much more mature, sophisticated way, is we're going to solve this bad boy here. Now, you could go ahead and try and log both sides, but I'm going to give you a big fat hint. It's a lot easier if you divide both sides by any coefficients first, and I would definitely always try and do that. Whenever you take the logarithm of things that are multiplied, you have to split it up to the sum of logs, and it just sucks. So what is 12,000 and all this? That's got to be 4,096 probably would be my guess. That sounds like that's about right. Now at this point you might be going, okay, well I could just guess and check 2 to the whatever power. Well, let's actually solve this systematically. So you'll log both sides, 4096, then you'll log this side over here. Because we use the logs, the n minus 1 comes out in front. We've got log 2. The way we deal with this here is we go log 4096 equals n log 2 plus log 2. And then we can actually solve, let's see, I'm going to go log 4096. I'm going to subtract log 2 over here, and I get n log 2. And then finally, I can do some simplifying. In fact, because I'm subtracting these logs, I could actually say log 4096 divided by 2. And you know what? I'm just going to simplify now. I'll just do it up here, I guess. Okay, so this becomes n log 2 equals log of, that's got to be what, 2048. And then finally, n equals log of 2048, and I'll divide it by log of 2. Okay, so if I really want to know what this is, I can go log of 2048, and then I'll divide it by log of 2, and I get an answer of 11. Okay, so that's my systematic way of doing this, n equals 11. Likewise, we could have said 3 times 2 to the power of, and we would have had to sit there and guess, and we would have guessed and checked until we got this, and we would have done this sort of thing here, worked out, okay, well that's n minus 1, or oh, maybe that's a 10, I don't know, anyway. Don't worry about that part. We did it systematically, and I actually kind of like this method, even though it's a bit more work, it's much cooler. Okay, last question here. We also did some of these questions before in the previous section. So the amount, the mass as a function of time, is equal to the initial amount. It's a radioactive isotope question. So we've got 1/2 for half-life. We've got T over capital T. Now we're told it's got a half-life of 120 hours. How long does it take for a sample to decay to 10 grams? So we end up with 10 grams. We start with 200 grams. and it's got a half-life of 120 hours. So the way you can go about solving this with logarithms is you start by, if you said log both sides, you're almost right, but you want to get rid of coefficients. So I'm just going to write a little note here. Try and eliminate coefficients if you can. So we're not going to want to have this 200 out in front, and you can extend that the whole thing if you want. Cancel, cancel. Okay, so this becomes, and I'll simplify it, 10 over 200 is 1 over 20, and then this is 1 over 2 to the power of t over 120. Okay, so at this point you can see that 1 over 20 cannot be expressed as a power of 1 over 2, so we are logging both sides. When you log both sides, you can now bring the exponent out. You don't put brackets because of fractions. And now it's just a matter of solving. So one thing I'd like to show you, here's a cool little trick. If you want to do this, you can, although you don't always have to. Log of 1 over 20 equals log of 20 to the power of -1, which is log of negative log of 20. So I actually really like doing this because I find taking log of reciprocals to be very uncomfortable. So I'm actually going to use this to simplify. This becomes negative log of 20, and this will become negative log of 2. And the negatives actually cancel out, which is really interesting. So you can go log of 20 equals t over 120 log 2. So we actually just found a way to get rid of both of the reciprocals. Okay, anyway, finishing this up, we're gonna, let's see, we're gonna manipulate this. So 120 is moving to the other side, so we'll have 120 times log of 20, and then we'll divide by log of 2. At this point, you might take a second and think, is there a way I can simplify this? It looks like there should be some sort of rule, but it turns out there actually is not. Log of 20 over log of 2 does not simplify to something like log of 10. Don't get confused with the quotient rule. This is as good as we can get. Now, because this is a word problem and we're given things in grams, it probably makes sense to work this out to get an actual answer. So what we do is we go 120 log of 20, and then we'll divide the whole thing by log of 2. So that gives me an answer of 518.63. 518.63 ... And of course, we're talking about, in the question, we're given a half-life of 120 hours, so that is hours. Okay, word problems are great. I don't know why everyone hates word problems. I think they're fantastic because you can actually check your answer to see if it makes some sense. Does this make sense? So just do the finger thing, okay? See me up there? Okay, so after 0 hours, how much of this radioactive stuff should I have? Then I should have 200 grams. After 120 hours, that's 1 half-life, I should be half as much, so I should have 100 grams. 50 grams, 25 grams, 12.5 grams, and then if I want to get down to 10, I'm not quite at my 5th half-life. I've got a little over 4 half-lives. Each half-life is 120 hours, so 4 of them make 480 hours. So does it make sense that my answer is 518? A little bit more, but not quite 5 hours? I think it does. So there's our answer. Awesome blossom. Okay, so we are finished for this part. We will move on to part 2 later on, where we deal with solving logarithmic equations. It's a similar thing, but it's got a little bit more of a twist with domain restrictions. All right, thanks. See you on the next one.